So today we're going to be talking about the addition principle. And our first problem that we're actually going to look at and see how this works is that Congress consists of 100 senators and 435 members of the House of Representatives. How many members of Congress exist? So when taking a look at this, we can draw this in two sets, and they're disjoint sets. We don't have people that are members of the Senate and the House of Representatives at the same time. So you can have your first set being the Senate, and your second set being the House of Representatives, which we'll just denote by House. And looking inside of that, once again, we're drawing these disjoint, meaning they don't have any intersection. So the Senate has 100 people in it, and the House has 435. So another way we could have stated this problem is basically what's the union of the Senate and the House of Representatives, which we'll shorthand by House here. So what's the cardinality of that set? That's what those little absolute value symbols mean there. So cardinality meaning count, how many of them are there. So Congress is just represented by that. So basically we can break this apart into two different sets. So the cardinality of the Senate plus the cardinality of the House. So how many people are in the Senate plus how many people are in the House. So this 100 plus 435. And you might have thought, oh, that was pretty immediate. You didn't even need to go through this. And that's kind of the idea that we're going to use. So we're building up to a more general principle here. And so what this ends up giving us is that 535 is our answer. So our Congress consists of 535 members. So moving forward, what actually happens is if you have any k pairwise disjoint sets with n1 objects in the first set, n2 objects in the second set. You can even go on n3 objects in the third set, n4 objects in the fourth set, and so on and so forth until you get to nk objects in the k set. So that makes up our k different sets. And then you have the number of ways to select this object. We can actually figure that out. And to give a visual as to what happens, you have N1 in this first set, and so I'm not going to label the sets, but these sets can be all different sizes. You have N2 inside the second set. Remember, there's no intersection between any of these sets. And the reason why is that we have k pairwise disjoint. And so keeping that in mind, we can draw up all nk sets and label those amounts inside. Now, how many actually happen to occur if we're to select just one object from the k-sets? How many ways can we do that? Well, it's just as simple as adding up the number of elements in each set. So n1 plus n2 plus n3, n4 if we have it there, all the way up to nk. And we use these dots to kind of symbolize that. And I cannot emphasize enough the fact that we have to have k pairwise disjoint sets. That's the important factor here that gives us this addition principle. If there's no pairwise disjointness, and that means just any pair that you look at, there's no elements in common, we cannot use this principle right away. There becomes some different sort of formula that we need to work with. But as long as we have that, we can just simply add up the terms in each set and find our answer. So let's take a look at this for a couple more questions, see how this works. So if we have a character consisting of an uppercase letter, a lowercase letter, or a single digit, how many different possible characters exist? And so once again, to give us a visual, we can do our characters and kind of list them inside a box inside our set, make our Venn diagram. So we can have the uppercase letters, and notice there's nothing in common between the uppercase letters and the lowercase letters, because you can't have something be uppercase and lowercase. Even though they're both letters, there's a difference between uppercase and lowercase when it comes to characters. So there's 26 uppercase letters in the American alphabet, and there's 26 lowercase letters. And for our digits, let's think, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that gives us 10 digits in total, even though most people say 9 immediately. It is 10 because of that extra 0 there. Now, if we're to find our number of different possible characters, all we need to do is, so we'll write our cardinality of characters here just to kind of get in the habit of understanding this is a set essentially that we're looking at. And we could sum up our different sets. That's what the addition principle states. So this is just 26 plus 26 plus 10. And so 26 plus 26 is 52 plus another 10 makes 62. So this tells us that there exists 62 different characters. And looking at our last problem, you have a character consisting of an uppercase letter, lowercase letter, or a single digit. how many different 8-character passwords exist. So this is important in terms of security of our passwords. Well, when we look at this, you can't easily separate them into different sets immediately. It's not obvious. I mean, yeah, we could probably do, okay, those passwords beginning with an uppercase A, then those passwords beginning with an uppercase B, and so on and so forth, try and break it up that way. But notice there's a lot of different places that we have to account for. And keeping that in mind, I mean, you can basically write this out and show that you have 8 different blanks with an 8-character password. So with these 8 different blanks, there's something different that we're going to need to try and solve this. And so the addition principle can only take us so far. So we're going to need to use something other than this addition principle. And that's kind of the main thing. The addition principle, if we have these scenarios where we're looking for our a number of ways to select an object from one of k different sets, if those k different sets are easily able to be counted, then we can find an answer quite quickly. But otherwise, this can be a much more difficult problem, and then we'll need some different tools to handle that problem.